Hi friends, welcome back. Today we'll continue with the Bode plot. In the last lecture, we have seen two things. Basically, if your number of poles are at origin, then what will happen? If number of zeros are at the origin, then what will happen? Okay. I'll give the brief summary of that, then we'll continue to the today's lecture. In poles and zeros at origin, the magnitude provided by the poles is minus 20 n log omega dB. The slope is provided, this magnitude and slope, these are related to the magnitude spectrum, and this phi is related to the phase spectrum. So the slope is minus 20 n dB per decade. If your n is 4, it means you are getting minus 80 dB per decade. So this slope is due to this minus sign, it's decaying, and this one is rising. Okay, the phi over here is minus n pi by 2, here n pi by 2 in plus, here minus, and this is all about. Today we'll see the n number of poles and zeros, finite poles, not at origin now. Okay, so today's lecture heading is finite poles and zeros. So, but before that, let me clear one thing. Last time in the last class, I told you this: you have to shift 20. Any graph you have to shift by 20 log k. Okay, if you people have doubt, let me clear you today. Whatever we have seen over here, we have seen for the 1 divided by s to the power n. Over here, suppose k is given. Now the graph, the magnitude will be not simply 20 log omega. The magnitude will change now. It will be like 20 log k plus 20 log omega to the power minus n. Means in this case you will have 20 log k minus 20 n log omega. Okay, initially we considered only 1 over here, means instead of, if k is 1, log 1 is nothing but 0, so we were getting initially 20 n log omega. Okay, so what we are going to do in each and every problem, we are plotting this. Always we are plotting with respect to whatever we studied over here, but at the end we are just shifting the graph. Why? Because this extra quantity is coming. Okay, this extra quantity is going to aid in the magnitude spectrum always. If your k is 1, then it's 0. Then it's fine. If your k is 120 or whatever, so definitely you have to add that. Then only it will be proper magnitude spectrum. Okay, so I think it's clear you. Now let's come to the finite poles and zeros. So the open loop transfer function on g of s, h of s, I am taking 1 plus s tau to the power n. This is my standard format. Always I'll write in 1 plus s tau form. This tau is the time constant or the time quantities. Okay, over here this is my standard format. I'll always keep my transfer function into this form. Okay, now my next step is I have to take directly I'll take, it will be 1 plus j omega tau to the power n number of finite poles I'm taking. Okay, now my next step is I have to find out the magnitude of this. The magnitude of this j omega, लो भैया मैग्नीट्यूड फाइंड करते हैं यहाँ पे 1 plus omega tau square, isn't it, n times. This is nothing but the magnitude 1 plus omega tau square. Okay, fine, perfectly fine. The students who don't know about this, let me tell you, the magnitude of this thing is nothing but a square plus b square, real term square, imaginary term square. So the same thing I did over here also, you can check. Now the next step is I have to convert this magnitude into the log, dB. So it will be, you have to take 20 log of this, whatever you got over here. So it will become finally 20 n log, this will come over here 1 plus omega tau square. Okay, magnitude is over. Now let's find out the phase. The phase of given transfer function. Phase provided by the numerator is 0, and by the denominator it will be n times of tan inverse. It will be omega tau, isn't it? So when these two angles are in division, so you will be having 0 minus n tan inverse omega tau. This is my phase and this is my magnitude. Okay, so this is magnitude minus 20n log under root of 1 plus omega tau square. Here we have two cases. So चलिए इस पे अपन केस ठोकते हैं. So case number first is this omega tau, this inside of this under root omega tau, if this one is less than 1. If this one is less than 1, so what will be the scene? The scene, can I neglect this? It will become minus 20n log under root of 1. If this is less than 1 or less than 1, square of it will be again less. So overall I am getting here nearly 1. Under root of 1 it will be 1. Okay. So finally log 1 is 0. So magnitude you are getting is 0 dB. So case 1, if this thing is less than 0, so your magnitude will be 0 dB. And the case 2 will be, case 2, this may have omega tau may have greater than 1. Okay, how this can have? Which term is changing over here? Omega is changing over here or not? Isn't it? This frequency is nothing but the corner frequency. Don't worry, we'll discuss about this. So my point is over here, now suppose omega tau is greater than 1. Now I can neglect 1. So over here this will be 20n log omega tau square. I'm going to neglect 1. What you will get? You will get 20n log omega tau. Now if your omega tau is greater than 1, your magnitude का सकल सूरत ये ऐसा हो जाएगा minus 20n log omega tau. Isn't it? So two things you are getting over here. Over here you are getting 0 dB, no problem at all. And what about the phi? For the case 1 I'll get the phi value also. See, the phi is given this. Omega tau you are going to neglect. You will get over here 0 degree, isn't it? So phi is also 0, magnitude is also 0. But in this case the magnitude is like this. If you'll find out the what apna phase or slope, let's find out slope of it. So slope will be, slope is what? dm by d log omega. So it will be 20n. There will be no change in it. Okay, because when you will differentiate this with respect to log omega, you will get minus 20n dB per decade. Solve it by your own. You will get this one only. Okay, and the phi value you will get over here in this case will be minus n pi by 2. Minus n into 90 degrees. So these two things in the pole at origin case also the same thing, minus 20n we were getting there, minus n pi by 2 we are getting there. So here also we are getting the same thing. Only the changes are in the magnitude spectrum. There is a two condition in magnitude. The first one is if this omega tau is less than 1, then we'll get the 0 dB. Slope is 0. And the phi angle provided by the system is 0. But if this omega tau is greater than 1, then only we are getting some magnitude amount, and that is given by this formula. So when I put this formula into the question, you will get to know what is this chatta thing going on. Okay. Now the point is, what is the corner frequency? So friends, the corner frequency is the frequency at which the slope changes from one level to another. Now I'm asking one question to you. When the slope will change, why the slope is changing? See, in the slope formula where we calculate the slope, here is the kind of slope. The slope is going to depend on the n. N is the number of value. Number of value of what? Finite poles and zeros or not? Isn't it? N is the number of finite poles or zeros. If you are getting poles or zeros, accordingly your slope is going to change. So the frequency at which the slope changes from one level to another. So different frequencies we are getting to change in our slope. So those all frequencies we call the corner frequency. Okay, clear nahi hua? Koi baat nahi. Next, the corner frequency are finite poles and zeros location in the form of the magnitude. The corner frequencies are finite poles and zeros location in the form of magnitude. Abhi bhi clear nahi hua? Koi baat nahi. Let's come to this. Omega tau, these two cases we have seen. You people remember. Omega tau is less than 1. Omega tau is greater than 1. So omega is less than 1 by tau. In this case, the slope we are getting is 0 dB. We have seen. Phi phase provided by the system is 0 we are getting. When omega is greater than 1 by tau, the slope you are getting is minus 20 n dB per decade and the phase is minus 90 n. Okay. So, जो clear नहीं हुआ अब clear होगा. Okay. So come here, draw the Bode plot. The open loop transfer function is given. Now the corner frequency concept will be clear over here. Okay, Chintan Kakandi, everything will be clear to you people. Okay. So as I told you earlier, if you are given the format like this, always you will take the format in the form of 1 plus s tau. Isn't it? This is standard format. I'll follow this format only into this entire unit. Okay. So this is my standard one. So I'll take 2 common from this, 5 common from this and 10 common from this. I'll convert this into the standard format. So it will be like 10 into this 5 will come out. It will be square of it. So it is 25 directly. I am writing 1 plus s to the power 5 whole square. Chaliye. S 2 I'm taking out into 2. I'm taking 10 out also. It will be 1 plus s by 2. 1 plus अरे बोलो भैया 1 plus what? Where I am? S by 10. चलिए. So this is over. Okay. This is now standard format. Now see. You are going to start. Okay, let me resolve this constant. This 10 will cancel to this. Over here 25 by 2 you are getting. Correct? So this is 25 by 2. Now your transfer function is kind of 1 plus s to the power s by 5 to and whole square s 1 plus s to 1 plus s by 10. Okay. So now let me change the pen first. S equal to 0, your first point. Then S equal to 2. This is why 2. See, this is the frequency I'm talking about. The standard format is 1 by tau. Sorry, standard format is 1 plus s tau. So here this is the time constant. It means 1 by tau is nothing but your frequency. So I am writing here this is 1 by 2. Okay, means 2 is what? Our frequency or not? If your time constant is 1 by 2, your frequency omega will be 2. The reciprocal of the time constant is nothing but the frequencies. So how many frequencies you are getting over here? First at s equal to 0. The second at s equal to 2. The third one at s equal to 5. The fourth one is s equal to 10, means omega equal to 10. So you are getting 4 frequencies. First at origin, then at 2, then at 5, then at 10. So everywhere you are going to change your slope or not, tell me. We discussed that whenever you will get finite poles or zeros, definitely according to the poles or zeros, your phase will change. your slope will change, your magnitude will change, isn't it? So these all frequencies are corner frequencies. Is it clear to you now? Good. Now this is the K term, your K term. Now I have to draw the Bode plot. So let me start the drawing of this. I need magnitude and phase to draw it. Okay, but directly I can draw it. Please have a watch it, see. Okay, so come over here. This is in dB. The magnitude I'll draw. S equal to 0. The first origin you are getting. Origin, one pole at origin. Okay, so the slope provided by this is 20 dB or not, isn't it? Minus 20 dB per decade. Earlier we discussed, if you are getting number of poles at origin, they will provide you minus 20 n dB per decade slope. Okay, and the magnitude is 20 minus 20 n log omega. Omega is 0.1. This is the starting. So this will be plus 20. So you people know about this and will agree with me also. This is 20 dB starting point. Okay, this line will go like this. The slope of this line is minus 20 dB per decade. Now the question is, why minus 20? The answer is because of your pole, single pole at origin. The slope is minus 20 n. N is 1. So minus 20. Why magnitude is 20 dB? We have already done this. 20 n log omega. Omega is 0.1. Okay. So this is 20 dB. That's why 20 dB. So it will pass like this, like this. At omega equal to exact 1, it will cross the 0 dB line. Then next frequency I am getting at 2. So here let's take omega equal to 2 over here I am getting. So this is omega equal to 2. At omega equal to 2, what is going on over here? Just at omega equal to 2 you are getting one pole, isn't it? At omega equal to 2 you are getting the first finite pole. This is first finite pole at omega equal to 2. Omega equal to 2 is the your corner frequency. So this is pole and the slope provided by pole is 20 dB per decade by one pole. 2 pole minus 40 dB per decade. 3 pole minus 60 dB. So minus 20 dB again you will get the slope over here. So over here you were coming with the slope minus 20 dB per decade. Again you are getting the slope over here, that is 40 dB. This is 40 dB minus 40 dB. Okay, 40 dB per decade up to next corner frequency, that is 5. So here this is 5. Omega equal to 5. Omega equal to 5 you are getting 2 poles, finite poles. So per pole you are getting 20 dB per decade. So you have 2 poles. So you are getting 40 dB per decades plus 40 dB. So now initially you were at minus 40 dB. At this frequency, corner frequency, you are getting plus 40 dB. So minus 40 dB plus 40 dB, it's a 0. So you become flat up to next corner frequency. ये जा रहा है continuously like this at omega equal to 10. Omega equal to 10. रुक जाओ यहाँ पे. Omega equal to 10 you are getting single pole, finite pole, and single pole will provide minus 20 dB per decade. So this is minus 20 dB per decade. This is your Bode plot. Okay, because of this transfer function. Now this is not complete. Remember one thing, you have to provide shifting by 20 log k, and k is 25 by 2. So value of this will be 22 dB. So you will shift this entire graph at each and every point by 22 dB. It will become 42 dB at the starting. Each and every point you will going to shift. So this is your Bode plot. This is your Bode plot. So what is this Bode plot? The Bode plot is the game of the slopes only. The slope provided by pole, the slope provided by 0, the slope provided by number of poles and number of zeros at origin. So इसी का खेल Bode plot है. Okay, so I think it's clear to you people. So please now listen carefully. The slope provided by the n number of poles at the origin is minus 20n. Wait a minute, let me start again. So the slope provided by the number of poles at origin is nothing but minus 20 into n dB per decade. And if we are talking about the n number of zeros at origin, then it is plus 20n. N is the number of zeros, or n is the number of poles, whatever you are getting. So 20n dB per decade. Okay, this part is over. Now let's come to the next one. If you are getting n finite number of poles, the slope will be same whatever you were getting in the case of n number of poles at origin. So in the case of poles, always you will get minus 20 dB per decade. This is for the single pole I'm talking about. If 2 poles, minus 40, 3 poles, minus 60, 4 poles, minus 80 and all. Isn't it? Is it clear to you? And the slope provided by the 0 is plus 20 dB per decade. Plus 20 dB per decade for the single 0. And for 2 zeros, 40 dB per decade. For 3 zeros, 60 dB per decade, and like this. So please remember this thing. And the thing is, poles will provide you minus 20 dB per decade. Zeros will provide you plus 20 dB per decade. Okay. Now, maybe you people have some doubts. So in the next lecture, we'll clear it. Okay. चिंता करने की कोई बात नहीं है. जो भी if you have any problem, कोई भी दिक्कत परेशानी तकलीफ आफत संकट मुसीबत बला प्रॉब्लम समस्या आपदा विपदा ट्रबल दुविधा कष्ट कठिनाई, I'll clear you in the next lecture related to the Bode plot. So ఇంకా కొత్త విషయాల కోసం గెట్మెటిక్ ని సబ్స్క్రైబ్ చేయండి. ఏమైనా డౌట్ సాల్వ్ చేసుకోవాలి అనుకుంటే ఫేస్బుక్ లో మమ్మల్ని చూసుకోండి. Subscribe Gatematic for the new updates. You can find us on the Facebook for doubt solving. We'll meet in the next lecture. Till then, take care and bye.